We are now going to discuss Theorem 10.7 from the geometry textbook. This theorem states that in the same circle, or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So in other words, chords AB and CD are congruent if and only if EF, the distance from the center E, is congruent to EG, the distance of G from the center E. So in this circle, what this theorem is saying is that if we have a circle, and we have a center E, and we have chords AB, B is a little blurry there, and chord CD, AB is congruent to CD only if EF is congruent to EG. So we can look at it on this circle. So here we have the same diagram. We have chord CD and chord AB. We have EG and EF. And we're saying that CD is congruent to AB only if EG is congruent to EF. So why is this the case? Well, let's first assume that EF and EG are congruent. So we can then say that EG is equal, the length of EG is equal to the length of EF. Notice E is the center of a circle. So what we can do is we can draw radii from E to A if we so choose. And we can draw a radius from E to C if we would like to do that. We can do that as well. And these two radii are congruent because all radii in a circle are congruent. So we can write these two as being congruent. And at this point, we have a set of right triangles, CGE and EFA, both of which have one hypotenuse congruent and one leg congruent to each other. So therefore, we know by hypotenuse leg that these two triangles are congruent. Since they're congruent, we know that the third side, which is AF in one triangle and is CG in another triangle, are also congruent to each other. So what we have so far is that line segment AF is congruent to line segment CG. But what we wanted to prove was that chord AB was congruent to chord CD. How do we get there from where we are now? Well, all we need to do is to recognize the fact that EF is part of a diameter of a circle. And we already know from a prior theorem that if a diameter of a circle is perpendicular to a chord, then it bisects the chord. So actually we know that AF is congruent to FB. Furthermore, because of the same reason, we know that CG is congruent to GD. Therefore, we know that AF plus FB, which is equal to CG plus GD in terms of length, or in other words, chord AB is congruent to chord CD. And that was what we needed to prove going in that direction. To prove the theorem in the other direction, we have to assume that chord AB is congruent to chord CD, and from that prove that line segment EF is congruent to line segment EG. So if chord AB is congruent to chord CD, then because EF and EG are parts of diameter, we know almost immediately that line segment AF is congruent to line segment CG. Again, this is because AB is congruent to CD, and EF and EG bisect AB and CD because they are diameters. So we have this congruence, and just like in the previous case, we go ahead and we draw radii from the center of the circle to points A and to point C. like such. And we end up with, again, two right triangles. We've already proven that that AFCG, one of their legs are congruent. But what we've just drawn, CE and EA, are both radii of the circle, and because all radii of a circle are congruent, we have that CE is congruent to EA. So thus, by hypotenuse leg, we now have two congruent triangles, CEG and EAF, and because the two triangles are congruent, we now know that EF is congruent to EG. And that was what we needed to prove, that equal chords are equidistant from the center.